with your talk, which is now.
Oh, great. Thank you. Thank you all for coming. And let me start sharing the screen. Hold on. Yeah, okay. So I'm gonna talk about my recent work on log-concave inequalities. Can you all hear me?
I can, yeah.
Okay. Okay. So I don't know many of you. If you can try to be on video, I can actually see you. I think my setup with my setup, I can see you, and it would be nice if you could be on video and ask questions and so forth. So hello, thank you for being here. And this is a joint work with Swee Hong Chan, who is my postdoc, and and I'll tell you a lot about what we're doing. So the picture on the left is what I got when I Googled poset. I'm not sure what mountains have to do with posets, but that's how it is. Okay, so let's see. So we wrote a somewhat of a monstrosity paper. It's 71 pages in a tiniest possible font with the smallest margins I could get. It's a long technical paper, and you can see on the right I have a long list of items. That's just subsections of the introduction. Everything else is longer and technical. So what happened is we started proving some inequalities, and we just couldn't stop. We continue improving a lot of log-concave inequalities until we basically got tired, and until there was a point when Swee Hong needed to apply for jobs. So I basically said, that's enough. We need to finish this paper so you can get a job. And I'm going to talk about very small portions of the paper. I'm mostly going to be talking about linear extensions over here. Okay, and but I will mention at the end our results about matroids, and I'll talk about basically everything here. Is everyone okay with the plan? So do this or that if you have any questions so far. Everyone okay? Okay, good. All right, so I'm going to start by recalling some standard definitions. I'm going to talk about standards and inequalities. So let P be a poset on n elements, and I'm gonna fix an element Z over here, and that element is going to be fixed forever. I'm going to study linear extensions of my poset, which are bijections from the ground set X to numbers from 1 to n, so that the bijection is order preserving. That is, we always have L of X less than L of Y whenever X is smaller than Y in the partial order. Those are linear extensions, and I'll give you an example in a minute. And we denote by E of P the set of linear extensions, and by EK we denote the set of linear extensions, so that the linear extensions take value K at our special element Z. Okay? Any questions so far? Okay. So what we prove is that so Stanley proved in 81 the following inequality and the concavity for numbers n of k. N of k is the number of these linear extensions which take value k at element z, and that was rather surprising. It was I didn't write it here, but this was an open problem for a bit. People first conjectured unimodality of these numbers. Then they figured out that the log-concavity might hold, and eventually Stanley proved log-concavity. Okay, and that's a remarkable fact. So let me do an example just so that you can see. I'm sort of doing this slightly unconventionally. I think of numbers above as smaller than below out of convenience, my own convenience. And so this is a these are all curly brackets. And my element Z is the element in the upper right corner. So in that particular case, this poset has 5 linear extensions. They're all shown here on the right, and so we have number of linear extensions is 5. And if you look at the upper right corner, there is 1 linear extension where this number is 2, and there are 2 linear extensions when this number is 3. So the numbers are 1, 2, 2, and there is an obvious log-concavity in a special case. Is the statement clear? Yeah. Those of you who are not on video, you can push a button and you can also do that. Okay, good. So that's what we're going to study for a while, and that's our main result. So let us show you our generalization of that result. So what we did is we found a weighting which allows a generalization of Stanley inequality for numbers with respect to certain weight. So we say that a function omega, that's a weight function on X, is order preserving if order reversing. If we have that condition, so whenever one element is smaller than the other, we want the omega to go the other way around. Okay, that's my definition of order reversing weight function. And now that weight function was defined on the ground set X. So now I'm going to extend it to the whole set of linear extensions, and I'm going to extend it in the following way. I'm going to take a product of omega over all X, so that L of X is less than L of Z. Remember, Z is our element that was fixed forever, and we're looking at a product of omegas over all elements for which linear extension is small. And naturally, we define sort of weighted analog of Stanley inequality. We define it. Sorry, something happened to my mouse. We define weighted analog by yeah, I guess I'm going to have to do with that. We're going to define weighted analog as a sum over all linear extensions of the weight of that linear extension. Everyone okay with this? And now our main one of our results is this weighted analog of the inequality and omega of log-concavity. Give me just a second. I'm going to try to fix my touchpad. Okay, I think I fixed that. So, is the result clear? Yeah. So that's a generalization of the Stanley inequality, and in particular, where omega is identical 1, we get the usual Stanley inequality. And in order to prove that, we need to do something. It doesn't work. So this inequality won't follow from the original Stanley proof. I'm going to say a little bit about Stanley's proof later, but essentially, this inequality comes as a byproduct of the novel technologies that we invent, which we call a combinatorial atlas. Okay, and that's the same technology that's going to apply to many other cases. That's what we invented. Okay. So any questions about this so far? Somebody should ask a question. Okay.
Question from anybody? I think everybody is happy currently with the definitions. They seem to be very clear.
Maybe completely shocked by this overwhelming result. Okay, so let's move on. So I wanted to give you an example. So general posets are rather complicated, and it's sort of convenient to think of a permutation poset. I'm going to fix a permutation sigma, and I'm going to define permutation poset p sigma in the following way. I'm sort of I want to think of elements of the poset 1, 2, 3, 4, 5. And I want to think of sigma as a permutation matrix, and then, for example, 1 is going to be smaller than 4 because 1 is less than 4, and sigma of 1 is less than sigma of 4. Okay, so you can sort of think of that as a two-dimensional poset, and have inequality going in both directions. Okay, and it is a nice exercise. It turns out that linear extensions in this case are exactly lower ideals in my in the Wick-Brewer order in the Wick-Brewer order. So for a sigma, we're going to take a Brewer order, and we take a lower ideal generated by sigma, and you're going to get that's how you're going to get linear extensions. So so on the right, you can see in this big picture, that's an example of a Wick-Brewer order, sort of Wikipedia example of a Wick-Brewer order corresponding to the whole permutation group S4. Now, Stanley inequality in this case says that the number of the way to think of that is n of k is the number of permutations which is smaller in the Wick-Brewer order. So, or in human terms, you can obtain that permutation from the original permutation sigma by doing bubble sorting towards the identity. But those permutations should also have should also take value k at element z, and the log-concavity is going to be over k. So that's what Stanley inequality says. Everyone clear about this? Now what we do is, for example, we have Q analog, but rather non-traditional Q analog. What you can do is you can define some weighting. Our ground set is a set of numbers from 1 up to n. So we define weighting q to the I, where q is a fixed number between 0 and 1. And if we do that, then weight function on every permutation, nu, which is smaller in the Brewer order, is going to be a power of q. This is that power of q. And where beta is some parameter of a permutation. You're summing some elements in the permutation which are left or to the right of k. But it sort of doesn't matter what is beta. We do have it. There is some kind of deformation of Stanley inequality in this case. And what we're saying is that for every k, you still have the log-concavity in this setting. Okay, so there is no way to even approach that kind of result without a technology. There's no bijective proof or anything. And let me emphasize: this is a result. This is a deformation. This is not a Q analog. So there is so even though this looks like a polynomial on Q, I'm not actually multiplying any polynomial on Q. I'm evaluating polynomial for Q between 0 and 1. Okay. Everyone good with this example? I want to move on. Okay, good. So in order to understand how to even approach this type of log concavity, let's try to recap a little bit what did Stanley do. So this is sort of a small screenshot of the title of the original paper. And what Stanley did is he looked at Alexandrov-Fenchel inequality. I'm going to say more about them later. He looked at them and he basically says, okay, so an equivalent version of that, or currently from Alexandrov-Fenchel inequality, is log concavity for certain mixed volumes, which you can see written over there. So that looks very generic and benign. We have some log concavity for some volumes. You don't know what volumes, you don't know anything. And then this is actually a screenshot of sketch of proof from another paper he wrote, where he says, okay, the rest is actually pretty easy. What we do is we go back to the previous work I had turns out that the number of linear extensions is equal to a volume of a certain polytope called order polytope. Sometimes people call it a poset polytope. And you can sort of see that polytope defined by items A and B. There is a natural polytope which is obtained as a slice of a cube, whose volume is number of linear extensions of a poset divided by factorial. Now we split that polytope into two chunks. Remember, we have a special element Z, so we do a hyperplane. We restrict the polytope to the facets of the cube corresponding to 0 and 1 on that element. That's how we get our two polytopes. And once we have our two polytopes, he's basically saying, look, you compute mixed volumes. That's an exercise, and we're done. We apply Alexandrov-Fenchel inequalities in that case. Do you see what I mean? So the punchline is if you have Alexandrov-Fenchel inequality, just the tiniest amount of geometric combinatorics gives you the proof of Stanley inequality. Okay, I don't want to go into details about the volume. I just wanted to show you how simple is the proof. It's really a couple of paragraphs. The calculation is missing here. Everyone okay? Any questions about this? Any of that? Okay. So so essentially what we do is we provide a tremendous proof, or really complicated proof of the same result. And for that we needed to avoid the Alexandrov-Fenchel inequality or bypass it somehow. Alexandrov-Fenchel inequality is incredibly complicated. I'll say more about that right now. I'm going to say about that. But essentially, if you want an elementary proof of Stanley inequality, you need to be able to deal with Alexandrov-Fenchel inequality. So that's our next item on the list. So let me remind you, or if you have seen it, or tell it to you for the first time. If you haven't, then you'll be really confused. What Alexandrov-Fenchel inequalities say, and what they say is that if you have convex polytopes, in general, the convex bodies are just as well. If you have convex polytopes K1 up to Kn, the mixed volume is defined as a certain coefficient when you take lambda 1 times the first polytope plus dot 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 lambda. This is lambda n. The last polytope, and turns out that this Minkowski sum is a polynomial in lambdas, and you take a particular coefficient lambda 1 up to lambda n, and that's how mixed volume is defined. It generalizes the definition I had on the previous page. And what Alexandrov-Fenchel inequalities say is that we have this inequality for the mixed volumes, And the important things to look at are this K1, K2, K1, K1, and K2, K2. That's what you should be looking at. Okay. So, so essentially, either you repeat, so you can have all polytopes, or you can have the first one repeated, the second repeated, and turns out that this is sort of like arithmetic geometric average inequality, but in a much greater setting. Everyone okay with that? You're all familiar? Okay. And now what was in particular, as I mentioned on the previous slide, the sequence, if you take the first polytope k times and the second polytope n minus k times, then the sequence vk of mixed volumes is going to be log-concave. That just follows immediately from Alexandrov-Fenchel inequality. Okay. And for many years, essentially for decades, people in combinatorics, we did not realize how powerful this Alexandrov-Fenchel inequality. And here is a headline, or as much as headlines go in combinatorics. At some point, van der Waals conjecture was proved using Alexandrov-Fenchel inequality, and Van Lint wrote a popular paper with the headline, "The proof of the van der Waals conjecture, 2 proofs in 1 year." But in reality, as soon as people realize that Alexandrov-Fenchel inequality is actually super powerful, so in particular, when all convex polytopes are boxes, just boxes, you can think of those boxes as rows in your matrix. Once you do that, it is an exercise to see that the mixed volume is actually the permanent of that matrix. And permanent is pretty important for many things, both in computer science and in enumerative extremal combinatorics, all kinds of combinatorics. So essentially what this inequality is saying, is Alexandrov-Fenchel inequality, is that making a matrix to have equal rows and equal columns pushes the permanent down. So for example, for bistochastic matrices, the smallest permanent you can get is when it's a uniform matrix. All entries are the same, and that's exactly what van der Waals conjecture is saying. Okay, that's how the whole thing goes. I'm not going to talk about van der Waals conjecture. Is Alexander? Are there any questions at this point? Okay. So before I move on, let me mention one very important item, and that is equality conditions. Equality conditions for all kinds of inequality are super important. For example, if you're thinking of as a parametric inequality, which is a special case of Minkowski inequality, which is in turn a special case of Alexandrov-Fenchel inequalities, we know that for the parametric inequalities, both are extreme examples. So if you want to, for Minkowski inequality, this is also extremely well understood. However, for Alexandrov-Fenchel, it's in full generality, this is a major open problem, which was resolved in case of convex polytopes, was resolved by Schoenfeld and Van Hent. I'm gonna say more about their work later, but in a special case, they obtained the following result. So in a special case of, so they made the extra effort to derive explicitly what happens for other polytopes, which are polytopes used in Stanley's proof. So in notation of Stanley's inequality, they're saying the following. Suppose n of k is greater than 0. If n of k is 0 because of Stanley inequality, n of k minus 1, n of k plus 1 are also 0. So suppose n of k is greater than 0, then the following are equivalent. Even if you just read the first 2 items, you'll be impressed. What they're saying is we have equality in log concavity if and only if all 3 terms are equal. You see what I mean? So that's already quite spectacular. But in fact, you can actually, even from computer science point of view, you can figure out whether this happens or not, because they also derived a longer condition. It doesn't really matter what it is. F of x and g of x are sizes of lower and upper ideal. And we're saying that all you need to do is check certain inequalities in the poset, which allows you to check whether we do have this equality in log-concave inequality of Stanley. Everyone good with this? Now, if you're very sharp, you can see that this paper is also not a walk in the park. That's a major result with a major proof, and that was published on the archive less than a year ago. Actually, you can see November 8th. You have to look very carefully. So I learned about it by chance, and that was crucial for us. It basically says that maybe Stanley inequality is doable. Okay, maybe one can approach it combinatorially, which is what we started trying to do. So, unless there are any questions about equality conditions in this case. Okay. Anyway, I'm recapping this theorem here, and here is our result. Our result generalizes this equality condition to the weighted case. Just like we generalized inequality, we also generalize equality condition. And remember, that's a completely different ball game. Schenfeld and Van Hendel used rather deep geometric analysis. I mean, not which you need in order to understand the Alexandrov Fenchel inequality, and essentially all three items generalize like you would think they would. There is some leeway here. There are some constants which you're allowed to have, but that and there is some leeway over there. But essentially, it's exactly the same.
So if I briefly may, are you actually using their result in your proof?
Not at all. We're giving
an alternative proof.
Independent.
Okay. Which is then significantly shorter, right? Because
well, our paper is very long,
so it's there.
I mean, it's sort of hard to compare.
Okay, sure.
There's a lot of background and technical preliminaries are needed in order to get to each of those results. At the end of the day, the result, once you have the first 60 pages, the result in their paper is not so hard.
I see.
I mean, it's an important application of that tool. Actually, the main applications of what they do. And just to address your question, yes. So what we do is we develop our combinatorial atlas technology allows us to give a completely independent proof of the Schenfeld-Van Hendel theorem and simultaneously proves our generalization. Okay, that's what we've been doing, and now let me take a kind of. I'm going to spend one slide explaining to why I wanted to do this. I don't usually work on log-concave inequality. That's not what I do. I basically study other type of combinatorials, including geometric and enumerative and algebraic. But what happens, I'm really interested in problems of the following kind. Given a function, which is a difference of Sharpe function. And if you don't know what Sharpe function, think of a difference of two numbers, each of them counting something, counting combinatorial objects. You're subtracting numbers of combinatorial objects, and you know that this difference is always greater or equal to 0. You just know it from Stanley's inequality. Does that mean that the difference have a combinatorial interpretation? That's a very deep question, which comes from enumerative combinatorics, and in this setting, it's phrased in computational complexity. language. But in reality, what we're asking is, are there some sequences that you obtain which do not have a combinatorial interpretation? So I wanted to particularly address this Stanley inequality, which, as I mentioned before, traditionally came from Alexandrov-Fenchel inequality, and nothing is simple about Alexandrov-Fenchel inequality. So I was hoping to resolve this problem for Stanley's inequality. So either find a combinatorial interpretation or show that it doesn't exist. And I'm not going to go into details of how can one, even in principle, show that some combinatorials don't exist. But a long story short, I failed. Basically, I cannot tell you either way.
Sorry, if I may briefly, you say you want to find a combinatorial interpretation of this difference.
Yeah.
How does this imply that it's in Sharpie? Because I mean, depending on the interpretation.
That's how I define combinatorial interpretation.
Okay, okay, I see.
So combinatorial interpretation doesn't have a formal definition yet. You cannot disprove something you cannot define. Okay. In order to disprove it, we need some assumptions on the objects that we're counting that they're polynomially testable.
Yeah, okay, sure.
Yeah, so that's a super vague assumption. Anything you can think of, normal things that you can think of, satisfies that assumption, like 3 colorings of a graph or number of Hamiltonian cycles, whether each particular subgraph is a Hamiltonian cycle is easy to test. Counting them is hard, but that's how the game is usually played. Okay. So you want to say that the difference is counting something. Maybe it's going to take exponential time to do the counting, but each object one can test in polynomial time. That's what Sharpie means. Okay, good, thanks. And essentially, if you want to, the only results in the literature you can find are all positive, and they're basically saying, look, here is a combinatorial proof. Combinatorial proof gives us a way to count the objects. So if we can find the combinatorial proof, which is what I wanted to do in the Stanley inequality case, then we can resolve this problem in the positive. Everyone clear what was my idea? It's not a super deep idea, and it would be nice if I succeeded, but I failed, and there is a reason why I failed. I do not actually believe this difference is in Sharpie, but in fact, the same true for many other instances, for many other functions you can get. So later on at the end of the talk, I'm going to mention about matroids, but even if you have f of k is the number of k forests in graph G, so you have a connected graph G, and you can consider forests with k edges. Now, in that particular case, Adiprasita Kat's theorem says that these numbers are log-concave, and one can, this is the simplest case that I can explain, and one can look at the difference, and one can ask the same question. Is there a combinatorial interpretation for the difference? And you shouldn't expect to find any. Forests are nasty. Trees are nice, spanning trees are nice, forests are nasty. Okay, so let me mention that the numbers we're actually subtracting are themselves Sharpie complete, so you don't expect any nice formulas coming out of here. So, so the difference is actually Sharpie hard, and the only hope is that it's actually lies in Sharpie, and we don't know that. Okay, I think I'm done with complexity part. Everyone good? This was my original motivation, and I'm assuming I'll be working on this favorite open problem for the next 10 years or so, or until I retire or die, whichever comes first. We'll see. So to be continued. Now, as I said before, we wanted to find another proof or go around Alexandrov-Fenchel inequality somehow. And essentially, we needed to go over all possible proofs. And there's a bunch of them. We started looking at them with Swee Hong. And this is a picture of one of the earliest. It's included in Alexandrov's collected volumes, but there are many more. So there are proofs based on algebraic geometry. One early one by Khovansky is included in Baraga's Algebraic book. There is a proof, which is independent and roughly the same time. There is a much better Kavansky proof relatively recently, and it was clear that this is not going to work. There is no combinatorial way to think of those proofs, and then there is more proofs. There's a proof by Wang. There's a proof by a whole bunch of authors you cannot see. They're written in a very small font over there. That's an analytic proof. And finally, we found the right proof. The right proof was by the same Fenchel and Van Handel. That is the right proof of the Alexandrov Fenchel inequality, and that is the proof that we try to understand. So that's the starting point of our investigation. And so the question that we ask is, can we have this, and elementary is a complicated word. It's relatively elementary. Can we have this elementary proof of Alexandrov Fenchel inequality? Can we reverse engineer it, do something with that to get an elementary proof of Stanley's inequality? That was the first push that we started to do, and turns out that the answer is yes. However, that's not so easy. Nothing is easy in this area, and even though that proof is the simplest proof but can find, it works for polytopes, it does exactly what we want, it still it still uses linear algebra technology, which we needed to unpack, and we had to create a whole host of technical, the whole setup to allow us to do what we want and modify the proofs quite significantly. So I want to mention that ironically, the Fenchel and Van Handel who proved the equality condition for Stanley inequality, they did not use the same the linear algebraic proof that they did. We used their earlier proof to reprove their theorem. They used another approach, much harder, or much more involved in some sense. So I hope Ramon forgives me for quoting his this is an email he wrote to me, where he says that initially they developed this proof because they wanted to understand equality condition for Alexandrov Fenchel, but that became the failure and it's impossible to do, and they gave up on it. So the punchline is that for Stanley inequality, it actually works very well. We could do it. We could circumvent some geometry that was an obstacle in their approach by doing combinatorics and obtain equality condition in the same way as we reprove stuff and generalize stuff. So somewhat ironically, we used one paper of these guys to prove the major result in another paper. Okay, so let me start so I wanted to say a little bit about the proof, and let me start somewhat vague. Essentially, if you start reading Karim's interview, Tawfiq Mansour asked Karim, tell me about log-concavity and how you prove all these results in Diprasita Hukat's paper, and everything that Karim is saying holds until this point. Essentially, he's saying, oh look, the way to think of log-concavity as a result about matrices. Once you start putting it in results about matrices, they correspond to bilinear forms. They have geometric meaning, and that's and the rest is technical. I'm not going to tell you about Hodge-Riemann relations. Okay, so what we're saying is similar, except there are no Hodge-Riemann relations in anything I'm going to tell you. So I'll just tell you what do we do in place of Algebraic relations, and this is not earth-shattering. It also appears in Schoenfeld-Handel paper. We deal with matrices which are hyperbolic, and hyperbolic is this condition over there, which it says it's not maybe the most friendly condition, but it's an elementary linear algebra condition. It's better to think of that in terms of eigenvalue, where it has a clear meaning. M has at most one possible positive eigenvalue counting multiplicity. It's an equivalent condition, but positive eigenvalue doesn't really tell you much about inequalities, and the hyperbolic condition does. So proving that lemma is essentially an advanced linear algebra exercise, not for undergraduates. It's not remarkable. But once you have those two notions, we can play with that, and that's our kind of frame, very basic framework. This is what we do. We prove hyperbolicity. So hyperbolicity is used to basically prove the whole result by induction. Instead of we make a kind of, it's the usual kind of thing when you have to use a strong induction, much stronger inductive assumption to prove a result, because weaker induction assumption doesn't work. So what we do is we prove hyperbolicity for bigger poset from hyperbolicity for smaller posets. We construct certain matrices corresponding to posets, and then we prove hyperbolicity by induction. And now, once you have hyperbolicity, log-concavity follows easily by setting vectors v and w to be characteristic vectors of what you want to compare. This is a general approach. It kind of works in all cases. However, the one eigenvalue condition, one positive eigenvalue, is actually quite important because that's used at the end. Somehow, the step of induction is a generic thing which is technical and can work, but doesn't actually require any computation. It's a very we have a very general setup to prove the step of induction. The base of induction is where the inequalities that you've seen, all those order reversing weight comes in. And in order to establish that, we need a target base. Okay. Are there any questions about? Well, it's sort of hard to ask questions when I'm being very vague, but you can still try.
Is that related to this Lorentzian property, where they also talk about one positive or at most one positive eigenvalue of certain polynomials? It is
related, but the connection might seem misleading. In some sense, what we do is a non-commutative generalization of that. It's highly non-commutative, and it is true. We're writing a follow-up paper where we can prove that everything that Lorentzian polynomial paper does is a special case of what we do, but that itself is not super obvious. But in reality, we use none of that at all. We do everything completely from scratch, and that's because the Lorentzian polynomial technology does not actually apply to establish Alexandrov, Fenchel, or anything like that, because of the so essentially, to put it in sort of trivial language, Lorentzian polynomials are commutative, and they in order to understand what's going on, what they do is they take derivatives. You need to take partial derivatives. In non-commutative setting, you don't have those. So rather than try to go from Lorentzian and find non-commutative generalization, we went from Alexandrov, Fenchel in a completely opposite direction. Simplify rather than generalize. So I do not have too much time, but I do want to mention that the way to think of what we do in this particular case of Stanley inequality, we come up with an acyclic digraph. We have for every, so the vertices of a digraph are going to, there's a lot of them, and they correspond to kind of partial linear extensions or pairs of partial linear extensions. It's rather involved, but the key thing to look at is are the matrices corresponding to vectors, to vertices of that digraph, and these matrices are going to be hyperbolic. That's what we're proving. We're proving that some matrices are hyperbolic, and the dimension of this matrices is 2 times the number of elements, and we also have some negative vectors, and that's pretty important. This transformation T, which corresponds to an H, which is to get back to you about Lorentzian polynomial, it's an example of derivative. This is so in Brandon Hu technology, all those maps will be identity, and they're very much non-identity in our case. So what we do is we establish, this is just cut and paste from the paper, theorem 5.2, is a very general condition for this graph, so that one can show that matrix is corresponding to vertex V is hyperbolic if all out neighbors are hyperbolic. So that's what I said about induction, and that's a very general theorem. I'm not going to tell you what these properties are, inheritance property and pullback property, but the way to think of that is those are some linear algebra properties. And so at the end of the day, everything using this theorem, everything reduces to base cases. And in the base cases, we basically have one special element and two other elements. So, and you look at all possible posets on 3 elements, and you check the inequality in all the cases. That's a routine thing. So, and you need the eigenvalue condition. That's pretty easy to check. Those are essentially we're getting some. So remember, this is 2 times n minus 1. So those are 4 by 4 matrices, and eigenvalues of 4 by 4 matrices are pretty easy to compute, and they have a whole bunch of zeros also. So this is a nice slide. That is not a nice slide, and I do not intend for you to read any part of that. Essentially, this slide summarizes what we're doing, how all those matrices are defined, and all those vectors, and that's somewhat. I understand that this is somewhat horrendous. And it's also may seem a little pathetic. The original Stanley inequality is proved in such a nice, elegant way. Why do you need to go in such a lengthy technical details? Well, you know, if you want to generalize something, if you want to understand something, that's what you do. So the picture on the lower right corner is giving you a vague idea what my acyclic graph looks like. It contains elements. So in those blue boxes, you have a lot of pairs of partial linear extensions, which are all mapped somehow into pairs of linear extensions of smaller size, and it all goes until nothing is left. And that's all I'm going to say about technology and the proof. Okay. Patrick, how much time I have?
Essentially as much as you want.
Okay, so, I don't want as much as I can claim, but I'll speak for another 10 minutes maybe, and
that sounds very good. Yes.
I'll tell you a little bit more. So let me. So in this picture about Stanley inequality corresponds to the t equal to 1 case. You can see that there is a parameter t over there, and that's important. The parameter t actually is mild enough to allow reversing the graph and obtain equality condition. So we do have to take limits in order to prove Stanley inequality and weighted Stanley inequality, but that's limits are very mild. On the other hand, if we do have in our setting a variation on the SVH proof, which can prove Alexandrov Fenchel inequalities, and there the issue is that you actually need to take a lot of limits if you want to prove the Alexandrov-Fenchel inequality. Essentially, it is a crucial condition which goes back to Alexandrov original 1937 proof. Is the polytopes have to have the same normals, so and the same combinatorial structure, and you cannot do induction on that. You really have to take limits. You have to be able to add small faces. You have to able to remove the small faces. There are issues in doing Alexandrov-Fenchel inequalities just for polytopes. You have to take limits, and that's why the first SVH paper does not actually give the equality condition, because it can. Taking limits, when you take limits, you can have strict inequalities giving you in the limit an inequality, and there's just no way to get around that. That is also what happened that is also what happens. I didn't say that, but the reason why we couldn't prove my results in Sharpie is because we do have this limit when t goes to 0. So somehow proving that something can be counted combinatorially doesn't work when you take limits. So the proof, even though it allows you to get equality condition, it does not allow you to get combinatorial interpretation. But I do want to mention that for matroids, our construction simplifies tremendously. So essentially, we got a really complicated result for linear extensions, and then once we had that result, we started reproving a host of other poset inequalities I mentioned at the beginning. I'm gonna since I do have a few minutes, I'm gonna show you. And in those cases, the combinatorial atlas becomes much simpler and can be generalized further. So let me spend a couple of slides just discussing various Mason conjectures and the recent results about that. And I'll mention on the next slide what we proved. So for matroids, we have log concavity for the number of independent sets of size k. That is a famous result by Deprasita Hukats, and I couldn't believe that this can even be proved when I first saw it. It's just way too remarkable, and it was clear to me right away that you can't let it stand. You need to give a combinatorial proof of that result, which is what we have now. So after that result was proved in a later paper, Schroeder and Bank proved a somewhat strong inequality where you see there is this factor 1 + 1 over k added. This is one can think of that as one-sided ultra log concavity when you have only one part of the binomial coefficients. And all of this used, both results use a tremendous amount of algebra. In a more recent result, which is sort of independent by Anari Liu, Ovesgaran, Vincent, and Brandon Hu, this is a relatively elementary proof of ultra log concavity, where you see in addition to 1 + 1 over k, another factor 1 + 1 over n minus k. That's how I want to write ultra log concavity. It's completely equivalent to the version that you might already know. And that's where things stood until our paper. Any questions about the past result? I went through them super fast, but I'm assuming many of you have seen this before. Any questions about this? Okay. So here is what we proved. We extended this Mason inequality, and I need to define to you how we do that. So so for every independent set, we define the set of continuation of the set to be elements which you can add, so it remains independent, and then we define equivalence relation. on different continuations. So remember, you have, if you think of if you think of vectors in a vector space, those are new vectors that you can add, but those new vectors can create the same subspace which is bigger than this one, or can create a different one. So you want to have equivalence relations depending on whether it gives the same or not, roughly speaking. And we call equivalence classes, we call them parallel classes of independent set S. And finally, denoted by par of S, the set of parallel classes and P of K is the maximum number of parallel classes over all independent sets of size K. I know that's that's a mouthful, but the way to think of that is this is something smaller than n minus k. The largest number you can add are all the remaining n minus k vectors to independent set, and now we have we split them into chunk, and we can and we're counting the chunks, and that's our refined log-concavity for matroids. What we prove is that this 1 plus 1 over n minus k can be replaced with P of k minus 1 minus 1. And that proves what we want. Now, I want to mention, so this was a bit of a mouthful. I want to mention what happens for a graphical matroid. If you have a graph, if you draw some kind of tree in the graph, and you remove two edges, you're going to get 3 connected components. So so my parallel classes are going to correspond to edges that you can add depending on what connected components you create. So there are 3 types of edges you can add. That's the 3 over there. And now we have our refined inequality is saying that, so because this number 3 is very small, when you substitute into the formula, it gives you factor 3 over 2 in this case. So in this particular case, when k is equal to n minus 2, the ratio that you get in the log-concavity, this ratio is roughly by a factor of 3 over 2 greater than what you would get from the strong base inequality. You see what I mean? So that's just very explicit way for us to show how much more powerful is our inequality compared to older inequality. And in fact, we can show that this refined inequality, so this inequality is an equality if and only if the graph is a cycle. So you cannot improve it better than that. For other graphs, it's you're not going to get you get strict inequality. And finally, I want to mention the game that we play. Remember, in this, since we reprove the inequalities in a smart way, we also can get equality conditions. In that particular case, for the strong log-concave inequality, Murai, Nakauka, and Yazawa did prove that equality condition appears if and only if the girth is greater than k plus 1. The girth is the size of the smallest circuit, and what we prove is a refined version of that. So we also reprove that result, and we prove a refined version which says that in refined log-concavity appears actually in quite a few cases, and there are some conditions that needs to be checked. So the second condition is pretty easy when the weight function is uniform. but the first condition is a difficult condition which constrains your matroids, which says that the number of parallel classes has to be always the same. For all s. So, and incidentally, that's how we obtain the cycle result I had on the previous page. So I think my time is up, and that's all I wanted to say. Thank you all for coming and enduring this very long talk.
All right. Thank you very much for the talk. It was not enduring, I think. It was a good length as well. Do we have questions? That does.
You mentioned the equality condition for matroids. If you have a realizable matroid, does it simplify, like in the case of graphical matroids, to something which can be easier to describe than these two conditions or something?
If it's a realizable matroid, it can be restated in a simpler way using linear algebra. We do have in one of somewhere here in we talk about the case you can actually have general inequalities for this numbers p of k that we have coming but for matroids realizable over the finite field.
Yeah,
it's not a fantastic improvement, but we do have it. So as field goes larger, the improvement becomes exponentially weaker. But and in fact, graphical matroids are matroids realizable over the field with two elements, the binary matroids. But our general bound is not as sharp as you would get when you look at them as graphs, because connected components have kind of topological structures that you don't see in the realizable matroids. There is really not that much you can say.
Thanks.
All right. Are there any other questions? That doesn't seem to be the case. There's a few people thanking you for the talk in the chat, but no questions so far. So in that case, let's all thank Igor again. And with that, we are finished with our second talk of the day.